course. Thank you very much. Since everybody said from where you are coming, I noticed that the universities in France are changing name very many times a year almost. So this is not the last name of my university actually. Now it's Sorbonne Université, only one, and Pierre de Marie Curie doesn't exist anymore, I think, as a name. Anyway, so
Really?
Yes. So there was some joining, merging. Anyway, no more numbers. That's good. So the talk I prepare is kind of a mix of two talks. So the first part, some of you perhaps heard it already in the StatFis meeting 1 year ago, 2 years ago. But I wanted to present us here because there could be some connections with other fields touched in the other program, and also because it's related to memory. So this is why I wanted to talk about two problems in 2D coarsening. And then the main part of my talk will be about dynamics of disorder systems, the ones that we all like so much. But the motivation for the way in which I'm looking at these problems actually comes from quantum physics and from other programs I attended here last year and the year before that one. And so I will tell you what is it about a bit later in the talk. So I plan to have half an hour perhaps in the first part and the rest, depending on time, on the second part. So let me tell you about what's going to be. The first part, as I said already, is 2D coarsening, and especially what happens at the early stages of the evolution and the claim that we have that the system is approaching 2D critical percolation quite universally. And this is interesting for many reasons, but okay, I want to stress today the part that has to do with memory in these systems. And then the second part will be about mean field disorder spin models, and in particular when they evolve in isolation from the environment. And I will treat different cases that will belong to different classes now in terms of integrable or non-integrable systems. And of course, I will not have time to deal with the last parts, but issues that have arisen in the discussions, like memory effects in spin glasses or Kovacs effects in glasses, can also be discussed in terms of these models here. So the first part will be about a very well-known problem, which is just take a system for which you know the two phases. There are simple phases. One is disordered, the other one is ordered, but of a simple kind. And you want to take the system across the phase transition between the two phases with some protocol, and you want to know what happens, in particular, when you take it from the disorder into the ordered phase and how order develops. So this is a very traditional problem in statistical physics, material science. It has been studied for many years, and the dynamic scaling hypothesis allows to describe the long-time behavior of these problems with great success. But what I want to do is to focus on the early stages of the dynamics and link this evolution to the approach to critical percolation in 2 dimensions. They will only talk about 2 dimensions today. So there is a series of papers that we've written in collaboration with many people. I don't want to list them, but I just flashed their names over there. So as I said, it's the stochastic dynamics. The system is coupled to a bath. I will take as an example 2D easing model. It's the simplest possible case. I will do an instantaneous quench by changing the temperature of the bath from high to low across the phase transition, and hence I will start from a very disordered paramagnetic initial condition, and I will try to see how the system approaches this dynamic scaling regime that will eventually take it to order into the ferromagnet state of one kind or the other kind. For these problems, the dynamic mechanism that takes the system towards larger and larger ordering in real space is understood. It's curvature-driven. You will see some drawings later on. It's called curvature-driven domain growth, and this defines a class of universality, if you wish, in the kind of dynamics of systems that do coarsening, phase ordering kinetics, and domain growth. So just to set a little bit the notation, the Hamiltonian is the normal easing one. J is the coupling constant, is positive. spins are classical objects, take values plus or minus 1. There is a sum over nearest neighbors on the lattice. The shape, the geometry of the lattice will play a role later on, but imagine it's a square lattice for concreteness. And there is a critical temperature at a Tc larger than 0, in larger than 1 dimensions, in particular in dimension 2, which is what I'm going to consider. The coupling to the bath I mimic with Monte Carlo rules, for example, if we do simulations. And these are the normal, standard Monte Carlo, one of the choices that you can make to do Monte Carlo updates. Nothing very special about that. And the other parameter, which is the magnetization, is not conserved locally because I can have a move that takes these near neighbor spins, let's say, which are anti-aligned here towards a configuration in which they are aligned, and hence the magnetization that locally was 0 here, now it's 2, let's say, and there is a non-conservation of this object that will be the relevant other parameter for the phase transition in the problem. So this is what is called non-conserved order parameter dynamics, and at the end I will say something about other possible microscopic rules that one can use, but the rest of the presentation is about this case. So when one takes the system, say, from a very disordered initial state that corresponds to infinite temperature, let's say, so plus and minus spins taken with probability 1/2, no order, no correlations, nothing special. This is the initial situation. And we let it evolve at 0 temperature with the rules that I mentioned before. What happens is that there are regions that become locally ordered in plus or minus direction, let's say, for red and white. And these regions grow in time. So these snapshots correspond to later times after the quench at the initial time. And, these objects grow, and if your system size is sufficiently large, you will not see during the evolution in the simulation or in the calculation that none of the two colors conquers the sample completely. Okay, so you will see domains of the two kinds at any time after the quench, if in particular you take your system size to infinity. But if you consider your system size to be of a certain size, so there is a L here, capital L, that will with which I will call the linear length of my box, then I will see, for example, here that although none of the two colors conquers completely the sample, I can go, for example, from one end to the other one following a red island or a red region. And there is a spanning cluster or a wrapping cluster, because I'm using periodic boundary conditions in this case, that goes from here to there and comes back again on the other side. So although there is no net magnetization in this configuration, if I compute the magnetization, I would find 0 apart from fluctuations, because there is as much red as white in this plot. There is, though, a cluster that is percolating or that is wrapping around the system in this direction in this plot. That's a question? Okay. But when does this happen? Does it happen only at this very long time in this plot, or is it already present here? If I look here, I see that it is. If I look here, okay, it's a bit more difficult to distinguish with the naked eye, but it can also be studied more carefully with the analysis of the data, and this is what I'm going to do next. These are just snapshots at the critical temperature. I will not talk about the critical temperature, so just jump over that. So the question is, what happens during the very early stages of the t = 0 dynamics along this direction in time? So let's look a little bit more carefully at the configuration. At 0 time, there is no spanning cluster. I will signal the spanning clusters with a different color. There is none here. I go ahead, and in my Monte Carlo timescale, which I'm doing continuous time Monte Carlo, so I could do non-integer times. So even before one Monte Carlo sweep, I get a spanning cluster that goes from this side to the other and wraps around. This is of red color because you see it's surrounded by white. So this is a red cluster that goes one side to the other. So yes?
You were sort of earlier talking about the dynamics.
Yes.
So you're doing non-conserved.
I'm doing non-conserved dynamics. Okay. But then at the end I will show, but not show because I don't have the snapshots here, but I will tell you what happens with conserved dynamics.
So with non-conserved dynamics, why doesn't it become all red or all white?
Not immediately. It needs time for the system.
It will eventually.
It will eventually, with a proviso that I will discuss in a second. That will come in a second.
And there's no external field?
There's no external field. So the two states are perfectly degenerate. So the system can spontaneously break its symmetry towards up or down. But locally, it doesn't know whether it at the end will become red or white. So what it does locally is that, between inverted commas, it breaks its symmetry locally to choose red, but somewhere else it chooses white. And this is why you have domains from the various stages of the dynamics, and then these domains will grow, and eventually one will conquer the full sample or not. So you will see what happens.
In an infinite system it will not, right?
In an infinite system it will not. In an infinite system it will not, because it will need infinite time to do it, and time scaling with the system size. But for a finite system, you will see what happens. Okay, so I had this, but then it broke. A little bit later, there were some links, I don't know exactly where, that because of a spin flip, it just cuts the cluster in two, and it doesn't wrap anymore around the horizontal direction. But then if you go ahead, there is another one that appears, and you can see that it's fatter, right? That there is more mass, if you wish, along any of the directions. So there is no single link. There are two here. Here there is a single one that could eventually be cut, but I don't know. So this one is fatter than the other one. This one goes on and wraps in the two directions, but then it cuts in one direction and another one appears. So this is a white one that wraps in the horizontal direction this way, and then the black one cuts, and then another black one appears, and this one will remain. I mean, if I were to show you intermediate snapshots between this one and this one, you will always see these two. And if you let the system evolve for longer and longer times, what will happen in this sample is that there will be a white domain here and a black domain there, separated by a flat interface. So it will not magnetize this sample. It will go to a configuration with, a certain certain size of black or red and a certain size of white, but it will not completely magnetize. There will be this flat interface between the two, and this flat interface at zero temperature is fully stable.
What is your boundary condition?
In this picture here, in this one probably I'm not using any, probably I'm using open, because I don't see the things wrapping, or do I? No, I don't see them wrapping. So this one is open, but it doesn't matter. So the particular numbers that will appear in a second for certain probabilities and certain properties will change depending on the boundary conditions, but the feature will be there anyhow. So if you have open boundary conditions, so if you have periodic boundary conditions, you need two interfaces. If you have open boundary conditions, you will have only one. But it's not a qualitative difference of of the phenomenon.
Between horizontal and vertical.
No, there is no symmetry breaking between this. Just by chance, it happened to be this way, but there will be other ones that will have boundaries in the vertical direction.
But each sample has to choose either vertical or.
So
that's a kind of.
It's the early stages of the dynamics that for each sample will choose what the sample will do at the end of the dynamics. Whether it will magnetize completely, there will be some that will magnetize, you will see it in a second, other ones that will have these horizontal structures, and other ones that will have vertical structures.
What did you mean by flat interface?
Flat, horizontal, perfectly horizontal with no. Yeah, these are completely stable at zero temperature. You can see that with my dynamics you will not kill it. But of course, if I had a temperature, what will happen is that this phenomenon will last for a certain time scale, and then it will. So the question is, there is some percolation going on here. I already used the word many times. So in this sample that I showed, it's at 8 Monte Carlo steps that the final configuration is decided. So is there something particular happening at these 8 Monte Carlo steps? How can I characterize this time scale? Is the configuration of the system reached at this time related to the two-dimensional critical percolation? How the system reaches it? Does it influence the subsequent dynamics? Do these effects last for long?
When you add a little bit of temperature,
yes,
the interface is going to disappear or just roughen?
No, it will disappear eventually, but for very long time scales, much longer than the L to the 2 power, which is the normal equilibration time scale for this problem. So it will be much longer than that. So is it critical percolation? So there are methods or quantities that people have used in the past to characterize critical percolation that we can use as well in our dynamic configurations to see whether the geometric features and the statistical features of these objects are the ones of critical percolation. So for example, one of the quantities that people use in the context of critical percolation is the winding angle of the interfaces. So basically what they do is they look at the local tangent to the interface and compute the angle this tangent has with respect to another local tangent at a certain distance on the interface. So this is curvilinear distance. This theta is the angle. At lattice, this angle can take, on a square lattice, it can take only 4 values, but then when you take the average, this becomes a continuous object. And this is theta squared, the angle squared. And for critical percolation, this object is known to go like the log of x times a prefactor, and this prefactor takes a value, and this value is this object evaluated at kappa equals 6. Okay, this is related to stochastic Levener evolution, conformal field theory, can be computed in different ways, but okay, it's known.
What's kappa?
Kappa, it's a number. It's a number which takes the value 6 for critical percolation. So it's the kappa of the SLE. So SLE kappa is 6. And it has to do also with the C of the conformal field theories. So there is a relation between the two, a function that relates, the central charge of the CFT and the kappa. But for critical percolation is 6. For the critical easing model is 3, for example. And for other critical points, could be something else. Yes.
It's a kappa of something, and I didn't get
A critical percolation in 2D. So the value that kappa takes for a critical point of percolation, it's a parameter.
J over KT or anything like
No. No, it's the parameter that characterizes the critical universality class you are working with. It's like an exponent, also it's not an exponent, but okay, it's like an exponent.
It is
Yeah.
the central charge, right?
So it is the central charge, but it's not equal to the central charge. There is a relation between the two. So what you can do is to compute these objects, for different times on interfaces that you have during the evolution. And what you find is that at long length scales, these are different times, you have these straight lines as a function of log x, from where you can get the prefactor, and then you make a fit, and you find that it's very close to this 6. Here, the result is flat. Why is it flat? Because here is short distances. At short distances, you're just seeing, the normal curvature-driven coarsening of your domains. So it's the smooth domains. It's at long distances that you're seeing this percolation. Yes.
I'm going to restate. I think I understood that question. So would you know before you started that it should be this class, or is
No.
it like this happens to be the class that fits?
No, this happened to be the class. Okay, I'm showing the end of the story. So we started with this like 10 years ago, and 10 years ago we said, oh, look, it looks like critical percolation, and then, we did a lot of checks. But we cannot prove it. We cannot prove it analytically. It's an observation, if you wish.
Okay. Was that the question that you were asking? Or?
I was asking a more simple question.
But this,
No, just,
this is clearly a dynamical effect. Because, it's with this easy model, as you said, with an associated kappa equals to 3.
Exactly. So nothing to do with the critical point of Ising model.
Yeah, so it is a sort of, this kappa comes entirely due to the, it does it depend on the kind of protocol? No, it equals to 0, it doesn't really.
It doesn't depend on temperature, because at temperature, what will it do? It will roughen the interfaces, as you said. But this is at short length scales. So it may change what's going on here, but it will not change what's going on over there. The working temperature doesn't change this feature. The initial temperature doesn't change it either.
The MC rules?
The macroscopic dynamic rules? No. What will change the macroscopic dynamic rules is the time you need to reach this situation and the way in which you do it. I mean, the kind of dynamic evolution that you have towards this particular situation, but not the fact that you get it.
Sorry, Leticia,
Yes.
I missed how do you actually define this?
It's well, I can do it on the blackboard, but it's the same here. Imagine that I sit in this point, on this point. Imagine that the tangent to the interface points vertically there. Then I go to a different point. Here it points horizontally. So the angle is pi over 2, or minus pi over 2, depending on the convention that you chose. And then you go ahead, and then you do averages.
Okay. So then, I mean, is there any requirement that this kappa should be integer or can be any value? Or
for critical percolation is 6, for critical easing is 3. Now for other strange critical points with parafermions or whatever, I don't know. But for these typical cases of 2D criticality, there are these two integer values. Yeah.
Cutoff is the correlation length. You would expect that that's time.
Right, yes. So you see here there is the scaling of these curves, and this is the length, the growing length, the usual one, the t to the 1/2. So this part is completely determined by the normal curvature-driven growth with the t to the 1/2 thing. But this is what's going on here. What has gone on to arrive at this horizontal line that I have already that I'm already showing you here, it will be controlled by a different length scale, a different growth, a different kind of growth.
But your computation is performed on the largest connected cluster?
It behaves, in principle you can do it on all of them. But it's better to do it just on the largest one, so it's less noisy. The data are less noisy. But you could do it on both. We checked these data for the largest, but you could do it on both. Yeah.
If I were to try to calculate this based on the statistical mechanics of an interface subject to surface tension, I would also get a logarithmic behavior with a prefactor that depends on the ratio of surface tension to KT and something to the finite.
But there's no KT dependence here, eh? This is a number.
No, that's a fit.
Yeah.
It points to a finite temperature, right?
Yeah. No, here I point to 0.
Oh, this is 0 temperature?
0 temperature, yes.
Okay.
Yeah. If I can show you later the data for finite temperature quenches. I don't have it in this file, but I can show you how it wants. But it will not change this.
Also in curvature-driven growth, the surface tension cancels out.
Yeah. Okay, so about memory. Some of you asked me whether you see it and some other ones, whether the system magnetizes in the end or not. So actually what happens is that in some cases it does and in some it does not. So what I'm showing here is the probability of having at a given time, which I'm scaling with the system size, and then you will see why I do that, but this is not important. The probability of having clusters that wrap in the two directions, this is for periodic boundary conditions, this plot, wrap in the two directions, wrap in only one direction, either horizontally or vertically, so these are the green data here, the sum of the two, and this is diagonal because of the toroidal geometry. They can be also clusters that wrap in both, but then eventually they disappear, so these go to 0. But let's look at the values at the plateaus. So at the plateaus, the dashed lines here are fits, and are fits that yield these numbers. And between parentheses are the exact values for the probabilities, the same ones, at the critical point of percolation in 2D under periodic boundary conditions, and they were computed by this person in 94. So you can see that they are very similar, so they agree. And what you see is that in the long time run, these will disappear, so these will not count. They will become those over there because basically, okay, these will completely magnetize in the white direction. These will completely magnetize as well because these parts will be eaten by the red one and they will completely magnetize, so they will go eventually to other. But this will not. This will remain. And whether this one or that one or the full magnetized state is reached by a given sample, it depends on what happens at this stage, if you wish, of the dynamics, very early in the dynamics. And the way in which this time scales with the system size is via power law for this kind of dynamics with an exponent ZP, which is for the square lattice a half. Okay, this is numerical. It could be something else, but we find that a half makes a good job. And it depends on the lattice geometry. So if I do another kind of lattice, I will get another exponent. Okay, so it's an exponent that depends on the geometry of the lattice. It's not universal in this sense. It depends on the kind of macroscopic dynamics. If I do conserved, I will find a different kind of scaling here. It's more difficult to just extract an exponent, but it can be scaled. The data can be scaled, and the growing length can be read from those scalings as well. But very similar picture arises.
So what's early or late? How do I?
Look, if I use the system sizes that are typically used in these problems, you get 8 for this time, 8 Monte Carlo steps. So it's super early in these terms. Of course, if I used L that goes to infinity, this time diverges as well because, But since the power is very small, a half, then you get very short times for this feature to establish.
No, but I was wondering, should I be referring it to something else that happens? To say this is early time or late?
Well, with respect to the typical timescales of the usual coarsening that go with L to the square. So, for example, if you from dynamic scaling, you have the growing length scale that goes to t to the 1/2. So, the usual one, the one of curvature-driven dynamics, has a length scale that goes like t to the 1/2. So the ZD is 2. This is ZD. And if you want to more or less get an idea of what's the time needed to equilibrate your sample, you say, well, I need a time scale that goes like that makes my length go like L. So this tells me that Tx goes like L squared. While this time scale, because CP, this one, LP, let's call it, for percolation, goes like T to the 1 over ZP, and CP is 2, you very quickly reach the length scale of the system size with this length scale. So this is why you percolate very quickly, and then the coarsening continues over the percolating structure that you have established, and then very much later in time it will eventually equilibrate. Now this prediction for this argument for the equilibration time does not take into account the fact that there are these blocked situations.
2 or half?
Oh, sorry, a half. I'm sorry. Yes, thank you, Wilbur. Yes, I'm sorry. This 2.5 is. The fact that at 0 temperature there are these completely metastable configurations is not taken into account in this argument for the equilibration of the sample. So actually the equilibration time of the sample, well, for these kind of configurations, it doesn't occur. It doesn't equilibrate the sample. Or if you wish, it equilibrates half and half in the sense that, there's always this interface. If you forget the interface, then equilibrate.
So in those drawings that you have,
yes.
All the colored regions are fairly wide. I mean, when you're talking about, is it just that it's a percolating?
Yes.
So it doesn't have to be wide.
Exactly. So it's a good question. The probability for having many stripes, they're possible. But the probability is so low that you don't see them. So basically, it's like you have a probability here, but it's, the first significant digit is the 5th or something like that. So you don't see.
The green one, for example, could neck down to only one bond between two parts, and that would still count as a percolating path.
Yes. This one, exactly.
That's
yes.
all you need.
Yeah.
So for the red and the blue curves, you're showing finite size effects. So the time at which you...
Everything is a finite size effect. Because if I take L to infinity, I don't... Although this time is very short, it diverges anyhow. So...
but there's an additional scale here, which...
This one.
Sort of where you have... No, I mean... if I look at the blue curve.
These ones.
Right.
Yeah.
So how does, so that.
This is of the order of this L squared
That's
thing.
fine, is it?
Yeah, it's roughly of that.
Increasing
Kind.
as you
Yeah.
go through larger systems.
Yeah. Okay, so this is the part of, okay, this is, what did I write here? Well, stripe final states. Stripe final states were observed by Radnar Kaprivsky and students actually doing the same kind of studies at zero temperature evolution of the 2D Ising model, but at the beginning they didn't link with this percolative phenomenon. Then, okay, we talked about it, they realized it, and of course the results are in perfect agreement and can be understood in these terms. I mean, the fraction of final states with stripes that we were getting are in perfect agreement with these probabilities, or this probability, if you wish, that I'm showing here. So this is the connection with their work. Okay, so I more or less said everything that it's in this transparency here. It seems to be a quite universal feature because, as I said, it's also observed for any initial temperature which is above the critical point. There is also observed for temperatures that are in the low temperature phase anywhere. This exponent seems to depend on, well, definitely depends on the geometry of the lattice, and it does depend on the kind of microscopic dynamic as well. It would be nice to find a way to prove it, but okay, I don't know. There is a recent paper by Cardi who says something about it from the conformal field theory point of view, but it's not definitive. And for the concern of our program, well, if you think about these block stripe states, I have in the memory of what's established very early in the dynamics. This is a kind of memory, and it's definitely metastability because these systems are blocked in a situation which is not the best one, but they cannot get out of it.
Leticia?
Yes.
What happens if you start from a slightly off-critical concentration?
In the conserved order parameter case, it doesn't happen. So in the conserved order parameter case, for this phenomenon to occur, you need to have 50-50. If you are imbalanced, and I think you are in your experiments from the pictures that you sent me, then this doesn't happen. So you have, you have the kind of features that you have. It's not critical percolation. Sorry, excuse me. There is a big matrix that is the one of the more present component, and then drops within. Yeah, which is what just happened. Yeah.
In the graphs of the tangent angle.
Yes.
You have this flex place, which is kind of the curvature, kind of growth part, and then it goes over.
Right. Yes.
It's and you kind of know where this transition is happening.
Yes.
So when the linear or the log dependence starts in, how different do the configurations look from the final configurations? Is it obviously there's some could you, by just looking at pictures where you finish the curvature growth part and you just started the linear, could you predict whether it ends up in a is there a correlation or somewhat of correlation whether you end up in the horizontal or in the does it
No, I mean the horizontal is just what's going on at any time
No, I mean can you predict the final the morphology of the final configuration, or is this
I think you can predict it from here. I mean if you're at this time here.
Oh yeah, clear. Then from there onwards, it is basically already settled, and that is sort of where you cross over from the in this other theta squared work.
Yeah.
This is where you cross over.
This is
This curvature.
In distance, this is just what's going on when you compare distances which are nearby.
Oh, sorry.
And then you don't realize what's going on at long distances.
No, I'm just completely. Yeah, this is.
So locally, you just see the smooth curvature of the coarsening. It's on the large distances that you have this percolative geometry. Yes?
From third law of thermodynamics, the t equals 0 is not realizable. So can I understand it as a limit of t go to 0?
Yes, because you can say, as I mentioned, I can show you later some plots, but at finite temperature, what you will see is that this feature lasts for very long. So you will have, for example, something like this, very, very long, and then eventually these things will start disappearing because at finite temperature, these walls are not fully stable. There will be fluctuations that make them disappear. So there will be a time scale here that depends on temperature. I can show it to you later, and system size as well. That makes these disappear, and then the situation will be of this kind, and then eventually the system will completely magnetize.
In the limit of T goes to 0.
For finite temperature, I mean. So for any finite temperature, this will happen, and the time scale, will diverge with temperature when temperature goes to 0. The time scale for these to disappear.
Since this L to the 1/2 is so fast, I'm wondering, is it really the dynamics that determines it, or the initial state? So if you run the same initial state with different dynamical seeds, would you always generate one or the other?
You mean for the same initial condition with different seeds? We didn't check that. Yeah.
Otherwise, it seems like you have superluminous transfer of information, right?
It's true. It's true, but the only thing you need is you need to grow a super fat domain. You need to grow a domain that goes from one end to the other, and that is sufficiently fat not to be cut. So that has no red bonds in the terms of the percolation language, let's say.
Information has to travel a distance L.
I wouldn't say so, because it's like matching little pieces, no?
So then you are saying it was there already in the seed.
Yeah, but I think that the answer to your question, although I didn't do the experiment, is that you will not necessarily get the same final configuration, because look here, for example, at 0 time I don't have any percolating thing. At very short time I do have one, but then it breaks. It's difficult to, I don't know, but it's difficult to think that this is that it will happen for any noise in this way, and that exactly these steps will be followed for any noise seeds, for all noise seeds.
But you're thinking that you could do a measurement that on the very first step, some correlation function on that, and that
maybe if you do some difficult statistical analysis of the initial configuration, you can.
Maybe you can see it.
Yeah, so this was kind of what I was,
Yeah, I don't know.
Try to, or is there a phase, and this is why I got confused, but is there a phase in the dynamics from where onwards essentially the morphology of the final configuration is determined?
It's for sure this 8 Monte Carlo steps is true. I mean, after that one. But even before,
is there,
I don't know.
From where, because, then it's then the rest, and then, so, so the one possibility is it's already determined kind of in the initial condition. And the randomness doesn't really, doesn't make...
No, I agree. At the beginning we thought that it was at the initial time, and then we realized that actually, on the average you needed some time to get there. So...
critical quenches, right?
It's not a critical quench. It's a quench below the critical point. Yeah.
No, it comes to the density, it comes to magnetization.
This is non-conserved.
It's non-conserved, it's under no field. Exactly, no. If I had a field favoring one state against the other one, most probably this will disappear. It's like changing the concentration that Damian was asking. In the conserved case, if I don't have a 50-50 mixture, but 51-49, it will eventually go. It will not be critical percolation.
And when this thing, the very first step, is it exactly 50-50? Or is it...
In the magnetization case, no. In the non-conserved order parameter case, it's not strictly 50-50. It can fluctuate, but its fluctuations...
The question would be, is that enough information? If it were just slightly more than 50, would that be enough to determine this?
No, I don't think so, because, I don't think so, but, okay, I cannot,
Sure.
Yeah.
Naive question. It's obvious that it's percolating. Are there other models besides continuous critical percolation that you might have expected it to match if it didn't match that?
I match all the exponents of critical percolation with a very good precision. I should just show 2 observables, but I have many more.
What I'm saying is, are there other models of percolation that might have matched?
But okay, this is the
You could have expected correlated percolation.
exactly. It would have been more, yeah.
So there is this model which gets TC of Ising models right, which is a correlated percolation model. But this is not the same as that.
No,
that's why
no,
the
no,
kappa
no.
is so different. Right?
Exactly.
There's this, yeah.
Yeah. So I don't know. I would love to have an analytical way to see it. I think, in words one can say that there is, okay, this is what I wrote here. In RG language, it suggests the first approach to a fixed point that is not fully attractive, critical percolation, that acts at the true initial state and the subsequent departure via curvature driven. But it's words.
Sort of gets close to the critical percolation and then
it flows, exactly. This is but okay, this is just a description with words of what we see, so it doesn't add so much. Okay, so let me go to the second part, which, well, I will do it as, we'll see, okay, how much I can say. So the second part has to do with the quench randomness. It has to do with disorder systems, disorder spin interactions, we all know, but in finite dimensions they look something like that. But I like to work with the mean field models where every spin is coupled to all other ones in the sample, and where there are not necessarily only two-body interactions, but also possibly three-body interactions, and the interaction strengths are distributed according to some probability distribution. And instead of working with Ising or Heisenberg or XY spins, I'm going to work with continuous variables that are constrained with a spherical constraint. So let me do a drawing here we'll probably use later. Well, let's draw it this way. Okay, so my space is an n-dimensional space where I can consider that my spin lives. So this will be my big spin with n components. And each axis, which are n of them, in this space is one of the components of the big spin. And there's a spherical constraint, so draw it. The length of the spin is constrained to be equal to square root of n, because I impose that this is equal to n. Okay, so this is a spherical constraint. And this model is nice because it allows to write Langevin equations, continuous, so derivative equations for the evolution in time of the spin, and this makes life easier if you're interested in doing dynamics. Now, seen in this form, this big spin that I have constructed here, I can also think as the position of a particle on the sphere. So the particle will move around this sphere, and it will feel a random potential, which is generated by these terms here. The random potential may have, valleys, mountains, plateaus, things complicated, but you have to think about this picture wrapped on the sphere, right? Since the particle moves on the sphere, well, it feels this potential on the sphere. As I said, this way of thinking about it as a particle moving on a random potential, it's nice because it, for example, for my purposes now, it allows to think in terms of classical mechanics. So it allows also to include a kinetic energy and to construct a Hamiltonian which has kinetic and potential part. And for the kinetic energy, we use the usual form and say we give a mass to this particle. This is the normal choice. And from here, you can write Newton-Hamiltonian equations, Hamilton equations that look like this. So you have a force that derives from the potential, and then you have a relation between position and velocity given by the other equation. And these are the equations that control or govern the dynamics of the isolated problem. If it's not coupled to a bath, these are the equations that rule the dynamics of the particle. Now, if the system is coupled to a bath, I can do two things. I can do statistical physics in the normal way. I can do, the analysis of the partition function, or I can write Langevin equations, which we have done in the past, add dissipation, add a noise, and a usual noise, say, delta correlated with the temperature being the prefactor of the correlations of the noise, and a white bath of this kind, zero mean delta correlations. Now, in this general setting of the Langevin equation, I can think about the dynamics of the isolated problem by setting gamma to 0. So I switch off the coupling to the bath by killing this one and killing the noise correlations as well, which is like killing the noise. Or if I want to do, temperature cycling experiments or the Kovacs effect and so on and so forth, one can simply consider a time-dependent temperature here and see what happens. I will not do this second part, but I just want to say that in this context, it's simple to set the problem in this way.
Leticia,
yes.
How do I think of this, the inertial term in the spin context, or I shouldn't?
I guess not. I mean, but it came from there, the problem, and then it drifted into the problem of a particle in a random potential, and it's a problem that, of course, has relevance for vortices. Meheran knows this, and for many other applications. So, I want to just say that we know there are classes of universality in this problem, not in the sense of the critical point, but in the sense of having common behavior that roughly correspond to choosing only two-body interactions, only polynomial interactions, but which are given, only monomial interactions, but are higher than just two, so three or more, but only a one type, or tuned polynomial ones. So, for example, the sum of two and three-body interaction terms. And these three classes are distinguished by the number of saddles there are in the potential energy landscape, the character of the barriers between those saddles, and the kind of dynamics that they have. So these are the main three features that I want to stress here. So in the two-body case, for the continuous spins, there are only n saddles. These can be computed, and actually they are the directions of the eigenvectors of this random matrix here. So if I now, instead of using this basis, I use a basis where I have the eigenvectors, so say v1, v2, vn. Each of these directions is a saddle of this potential energy, and the minimum corresponds to the eigenvector that's in the direction of the last eigenvalue of this matrix, the largest one. So for interactions which are Gaussian distributed, the density of eigenvalues of the matrix is the semicircle law. For n going to infinity, it has an edge, and the last one is the one that corresponds to the minimum, and then they are ordered in height according to how you move in the spectrum from right to left, let's say. It can also be shown that the barriers are finite between those saddle points. In the higher monomial case, there are exponentially large number of saddles, and the barriers scale with n. And in this case, there are also exponentially large number, but the barriers scale with a power of n which is smaller than 1. So for this reason, and for consequences of this, these models are more in the class of spin glasses. These are in the class of fragile glasses, let's say, and these are in the class of domain growth. So this is similar, very similar to the ON model of coarsening in the large n limit. Yes?
Are there some from the third category that actually have special Bayer distributions?
If there is an edge in the distribution, no. Because, if the distribution has a finite support, there are certain details that will depend on the way in which the distribution goes to zero. The distribution of eigenvalues goes to zero at the edge. That will change certain things, but qualitatively the behavior will be the same. Now, if you have matrices with Levy distributions for the entries, for example, then you will have tails in these distributions of eigenvalues, and then things change. Okay? So let's Yeah, I should have said for finite support.
I'm sorry, I'm a little bit behind.
Yeah.
These barriers and so the energy wells and these things you're trying to go over, and this well corresponds to the whole n spin ground state of the system, local ground state of the global system.
So the absolute minimum, let's say, of the potential energy, let's think in terms of zero temperature so that we can talk about energies without any danger. So the absolute minimum would be the ground state of your system, but then there could be metastable states higher in potential energy density, and the barriers between those could scale with n in different ways. And so what I'm saying here, in this particular case, which is the one which is more relevant for the classes, is that you have barriers that scale with n, and you have many metastable states above.
Okay, so n is
n is the number of
it's not
spins.
The number of spins.
See, yes, it is. It is.
Of directions on a spin.
But it's the same. So the number of spins is the number of directions on these spheres as well. So this vector n, I'm constructing by ordering, if you wish, all the spins in a vector, and each component is one of the original spins. But now I think about all of them in this vector as a huge vector spin that moves on the sphere. So n is both the number of spins and the dimension of the vector.
And the ground state as an interpretation as the eigenvector of the matrix JG?
For the case with two bodies, no. Well, it's more complicated than that, yeah. It's not that I could say something about, this tensor here. No. Yeah. So, okay, so actually, this is just a comment more directed to you. I will do it very quickly. There is a way to make this classification into a formula, let's say, or to see this classification into a formula, and it has to do with the behavior of this object, where F is the correlation of the disorder potential. So the square brackets are average over the disorder interactions, the JIJs or JIJKs and so on, and it turns out that this ratio here, depending whether it's 0, grows or decreases with C, you can use it to classify the different kind of behaviors. But okay, just to comment. Let's focus on this case. So in this case, there is all the zoology of metastable states that we know for many years now. If we plot the potential energy normalized by the strength of the couplings, as a function of temperature, there are many different objects in this problem. So there is the equilibrium energy, so the ground state energy, that grows with temperature, in some way. There are metastable states here, many of them, until a threshold region where there are no more above this threshold here. It's known that this threshold is flat, so if you are sitting on a saddle point that is on this threshold, it's like a plateau in a mountain behind here, the Santa Barbara, so it's flat. There are many flat directions, we can count them, that's not necessarily needed now. And these states, this equilibrium state exists, and all these exist until spinodal, where they don't exist anymore, like in usual metastable situations. And the phase transition does not occur when these disappear, it occurs somewhere else. And there are actually a phase transition, two phase transitions actually, a dynamical one, below where the system is not able to equilibrate anymore if you do quenches of temperature and it goes to this threshold, or in between this region, this is the true static phase transition where what dominates is the actual equilibrium of the sample. So I don't want to go very much into the details of this. I just want to say that this model has a complicated potential energy landscape with many metastable states, threshold levels which are flat, a paramagnetic solution which is just a normal paramagnet, and many things are known. Just to say that it's a very complicated model. Nothing of this remains for the p equals 2 case. This is for p equals 3. For p equals 2, this it's like this is condensed here, and this is also condensed, and all this is not relevant any longer. So now I want to look at the dynamics of these problems isolated from the environment. And why do I want to do that? Because, from our point of view in this conference seems quite strange thing to do. But I want to do it because there is a lot of interest in the quantum community concerning the dynamics of isolated quantum systems with each other. And the idea is to try to distinguish the behavior of integral from non-integrable cases. And from my point of view, my main interest is that there are many claims in the literature that are associated to the quantum character of the problem that people look at, that to me are not quantum in nature, they're just isolated in nature. They have to do with the fact that the dynamics is done in isolated conditions, and that one has to distinguish these two cases, even at the classical level. But many of the properties that people claim they're very quantum, in my view, they are not so quantum. So this is why I wanted to do, their same protocols in classical physics. So, okay, this is just a list of motivations. People are doing quantum quenching called atomic systems, which is just changing a parameter in the Hamiltonian and see what happens next. They are looking at effects of quench disorder, many-body localization, and so on. And a big part of what I'm going to tell you now for the classical systems is motivated by these works that I started here with Robert Koenig 2 years ago, and now in the classical context with my collaborators in Buenos Aires and Paris. So in the classical context, I'm going to, in a sense, ask the old ergodicity question again, but in a setting of systems with a large number of degrees of freedom and with potential energy landscapes which are very weird, but we know very well at the same time. So let me introduce a little bit better the protocols. So the quantum people, what they do is they say, I want to start with a system which has a certain Hamiltonian, H0, and I want to initialize the system in a state that could be the ground state of this Hamiltonian, or could be a mixed state, could be something characterized by a density matrix at the initial time T0, chosen in some way. And then what they do is they do the evolution, unitary evolution of the system from this, say, initial state with an operator which involves another Hamiltonian, not the same as the one that was chosen to draw the initial state. Okay? So this is the quench. This is what is called a quench, a quantum quench. So the questions they ask is, does the system reach a steady state? If it does, is it described by a thermal equilibrium density matrix of this kind, for example, with some temperature beta final here that one has to fix, or the system has to fix in some way? Or do at least some observables behave as thermal ones, described by something like that? Maybe not all, but some. Does the evolution occur as in equilibrium, not only the final value, but also the time dependence of the observables? Or are there other kinds of density matrices, not of Gibbs-Boltzmann kind, that describe what happens in the long time run? So these are the kind of questions are asked, and these same questions can be asked classically. So I'm only going to translate in the sense of getting rid of the hats, so no more operators. So I have an initial Hamiltonian H0, and I will evolve with a different H. And I will initialize, for example, the system in a configuration. In this notation, I will initialize in a set of configurations that I will draw from a probability distribution, because this is handy for my purposes. So I will draw the initial states, many of them, from a probability distribution of Boltzmann kind at a given temperature, beta prime, the initial one, with this Hamiltonian, H0 here. And then I will evolve those initial conditions with no contact with any bath, and with this Hamiltonian H, which is different from this one here. So this is the protocol, is identical to what they do. And then I can ask exactly the same questions, and instead of writing density matrix, I should have written probability distribution here. But, it's the same. So just to tell you in more details, the kind of changes in the Hamiltonian that I will do will only concern the potential energy. could have changed the kinetic energy, but I'm not choosing that. I'm just chasing the potential energy. And just to do sketches, the potential energy, for example, can be changed in a way, say that you have some parabolic potential, some simple examples. Huh? I could change the spring constant of this potential and either make it thinner or wider. Or I can do a change that goes from a situation with one minimum to one with two minima, or the opposite. Or I can do something like this, or I can do something like that to flat. So these are just examples of what can be done. And it's not very difficult to see that in these changes, what you do is you either inject or extract energy via the fact that the position of the particle doesn't change in this very instantaneous quench that I'm doing. But the potential it feels, it does. So then its energy does change as well. So you can figure out very quickly that there are cases in which one extracts or one injects energy by doing this. Okay, so now what do we know about the structure of these systems? We can suspect that the cases with p larger than 3 will not be integrable because, they are so complicated, these potentials, it would be really a miracle that these problems were integrable. So if they are not integrable, what we expect is that there will be thermalization within the systems. This is the common law that non-integrable systems, because of the interactions they have within them, will be able to equilibrate and reach some Gibbs-Boltzmann distribution at some temperature, beta final here, that will characterize the behavior of the observables that you want to look at. Just like going from microcanonical to canonical in usual state mech. But let me forget a little bit about the threshold here. P equals 2 is integrable. And I didn't know that when we started to look at this problem, but I have to thank Olivier Babellon, who's a colleague of mine at in Jussieu, when I told him about this problem, because I suspected it was integral, but I didn't know how to show it. And then, it's a model that exists since long ago. And in particular, Karen Uhlenbeck found the conserved quantities in this problem, the constants of motion. There are n constants of motion in evolution. I will show the form later on. And so this is an integrable system. Of course, they didn't look at this problem from the disorder point of view. They were looking at it as an ensemble of oscillators and with different coupling constants, different spring constants for the oscillators. But after a little calculation, it's the same problem. And hence the question is, for this problem, there's no reason why Gibbs-Boltzmann equilibrium should establish. And again, in the context of the quantum systems, people have proposed to use distribution functions of this kind, which in a sense look similar to the Edwards ideas of granular matter in the past, which is to say, well, if I have n constants of motion, which are these I mu's here, that depend on the coordinates and positions of the particle, then let's extend the Boltzmann form to include in the exponential all these constants of motions with effective temperatures, beta mu's, and call this a generalized Gibbs ensemble and see whether this form describes or not the long-term dynamics of the system.
You would get this form exactly if you did, standard. If you assume that the system was at equilibrium, then you have basically n constraints. You have n Lagrange multipliers,
right?
And then you basically pull out the
Yeah. It's the natural form that you expect, of course, but it's not so obvious, especially in the quantum case. It's not obvious at all, and in this case, it's not obvious either.
Either because it has to somehow do something ergodic, so that
exactly.
That this is really there.
Yeah. So, there's a huge literature on this problem in the quantum world, but there is not so much in the classical one. So this is the kind of questions that I would like to answer. So I see that I don't have a lot of time and I don't want to bore you so much, but let me just flash a little bit quickly what we do, or what we did. So, as I said, we chose initial states from equilibrium at inverse temperatures beta prime, we tune this beta prime, because we know the potential energy landscapes of these problems, to be either in the paramagnetic phase, which is simple, or in the low temperature equilibrium phases, or in metastable states in the case of P equals 3. And then we let evolve the problem with a different potential. So the quench that we did is one in which each coupling strength is changed into a new one by a factor. So it's multiplied by a number that makes it larger or smaller, but they are all changed in the same way. So in the sense, what we are doing is that you have to imagine that if you had a rugged landscape like this on the sphere, we are contracting it, or we are expanding it by this common change of all the Jijs. Why don't I do a more drastic change where I really change all the Jijs? Well, because I would forget completely the information about the initial conditions if I do that. I mean, it would be a little bit too much. So I want to do a change that can make my system become able to escape from confining states, like this one, for example, but I want this one to still exist, at least for a range of parameters. So I don't want to change completely my potential energy landscape. And this can be done by changing all the couplings in the same way with a prefactor, and then tune the value of the prefactor, and different things will happen by this tuning of the prefactor. The bath is switched off, so it's like saying that I initially had a bath that allowed me to equilibrate at beta prime, and then I switched it off, and it evolved with a different Hamiltonian with these different Jijs. How do you solve this? Okay, there are different ways to do it. One is the usual one, going through causal Schwinger-Dyson-like equations. They look like that. They are a bit more complicated than the usual ones because there is information on the initial conditions that is hidden in these objects here. There is an extra equation. There is a little bit of replicas in this calculation, but okay, this is exact. There's no approximation here, and these equations are exact in the end going to infinity limit. The kernels that appear in previous equations are known, and they have different forms depending on P being 2 or 3, and this makes the full difference between the two systems. It's not obvious to see it from here because the structure of the equations is the same, but having a factor, a power 1 or a power 2 here and there and here and there makes the system behave very differently. So those equations can be solved numerically, but they can also be solved analytically in different limits. And for the P equals 3 case, what do we find? So I will just show you rapidly the conclusions for the P equals 3 without showing you how we prove it, because I want to go to the P equals 2, which is more interesting actually. So one can draw a phase diagram of this kind. So here there is the parameter that controls whether you inject or extract energy. I don't change the mass, so forget the mass here. This J over J naught is the strength of the final interactions over the strength of the initial interactions. Okay? So on this side, we extract energy. On this side, we inject energy. And the separation is at 1, where there is no quench. So here, I don't do anything to the system. And the vertical axis controls the initial condition. So the initial condition is above the critical dynamic temperature, above this dashed line, so it's very disordered, or it's below that temperature, below this dashed line, so it's in a metastable state. So here I start from metastable states, there I start from paramagnetic situation. And I see that there are 3 phases basically in this plot that can be obtained in different ways, and these 3 phases are characterized by the behavior of what happens to the self-correlation functions, what happens with the correlation function between the time-dependent and initial configuration, something that the quantum people would call fidelity, what happens to the linear response, and so on and so forth. I mean, the same observables that we use for usual glassy studies. And the main features are that in both green and white regions, the system is able to equilibrate to a Gibbs-Boltzmann distribution with a final temperature beta F that can be computed in different ways, but is the same for all observables in the sense that, for example, say in this white region here, the system behaves as if it were a paramagnet, I know which is the expression of the paramagnetic energy as a function of temperature, and from there I can get the temperature, and then I can do, for example, fluctuation dissipation measurements of correlations and responses, and notice that it is the same temperature that controls the relation between the two. I can compute the kinetic energy of the problem, and I notice that is equal to TF. And so everything works normally, as in normal equilibrium at beta F, in this white region here, in a paramagnet. It also works in the same way in this green region, which I call TAP, is the region of metastable states. By the quenches, what we are doing is just starting from a nice metastable state, changing it by, say, moving it down and opening it up, but the system remains within it, between inverted commas. And the change in the potential makes the value of beta F tuned to a value such that the system remains in equilibrium within that state. So here and here, the interactions are such that the system can equilibrate after the quench. In the orange part here, it's funny because what we are doing there is we are tuning the parameters of the quench such that the potential energy of the system after the quench is just at the threshold. So I'm putting the system at the threshold with this quench. And okay, for those of you who know about the dynamics of the p-spin model, on the threshold, because the potential energy is flat, we don't expect equilibration, not even with a bath, and without a bath it doesn't equilibrate either. But the dynamics is very similar to the one that we know for the relaxational dynamics with a bath. There are two temperatures, we can compute them. In a sense, there's no big surprise about what's going on in the p equals 3. The particular form of the phase diagram, okay, one has to figure it out and compute it, but everything happens as expected. Yes? Okay, so p equals 2 comes next. So this is just to say that p equals 3, we can do it in all cases and compute everything, and consistently with the expectation that the system was not integrable, we find equilibration in the cases where the system should equilibrate. On the threshold it should not, and it does not, and that's fine. So now I'll jump how we prove all this. Now what happens in p equals 2? So in p equals 2, there are, as I said, there are many things which are known about the potential energy landscape. It's dominated by these directions, which are the eigenvectors of the interaction matrix. There are n of them, so there are n saddles. The barriers between them are order 1. The absolute minimum is the Vn. This is known from many, many papers. Now, from this paper, now in the classical mechanics literature, the motion of a particle on a sphere with harmonic potential is an integrable problem, and the constants of motion are these. Okay? So lambda are the eigenvalues of the interaction matrix, S is the position, P is the position. They are already in the directions of the eigenvectors. They are projected on the directions of the eigenvectors, but these are the forms of the constants of motions. There are n of them. One is the energy. Well, a linear combination of this is the energy, and another linear combination of this is constrained to be 1 because of the spherical constraint, and all the other ones are independent. Now, this problem is almost quadratic. So, if you write the Newton equations on the basis of eigenvectors of the interaction matrix, so this is mass times acceleration. This part is like a harmonic potential, so harmonic force, let's say, but there is Z, which is a Lagrange multiplier that imposes the spherical constraint, and that makes this problem slightly nonlinear, because Z depends on S. Okay? So Z is not independent, it's a function of time that has to be fixed by imposing the spherical constraint. So it's the only source of nonlinearity in this problem. Yes?
But since you have this, I mean, you have these integrals of motion that are in evolution. So, I mean, this should have actionangle variables, right?
Say it again.
It should have actionangle variables. You should
yes. Yes.
So you would have. So you wouldn't really need the spherical constraint because this is you have the manifold, you have the n evolutions. You basically phase flows of the different thetas.
Yeah, I agree. This has been studied by the people in the classical mechanics community, but for n equals 2, 3, I want n going to infinity. So it's a problem that has been studied, particularly by my colleague Babylon, and it's very nice. I can show you things that they have, but they are more focused on the finite dimensional problem, right? And I want to do the n going to infinity. And I want to ask questions about the equilibration that they are not interested in, or they were not interested in.
That at least you could base. But then, of course, the question is what happens to the dissipation, the Langevin forces when you translate this into the...
I don't have Langevin forces.
No, not yet. Okay.
Ah.
Yeah, okay. No. Okay. But so we will talk about it.
Okay. Yeah. So there, thanks to this fact that you can almost linearize these equations, there is another method to solve this problem, which has to do with dealing with these equations directly, not going through the correlations and responses. And there are some tricks that appeared in particular, for example, in this paper on the quantum context, but it's very similar and can be adapted to this one, that allows us to have a different angle to solve this problem for finite n. Because here we only have information about n strictly infinity, but we also want to have information about finite n, and I can tell you why if I have time or later in private discussions. So anyway, the phase diagram can be drawn as well, can be obtained. There are three phases like before. This again is energy injection or extraction. This is initial conditions. There are ways to characterize these three phases, but in none of them the system reaches thermal equilibrium a la Boltzmann. This can be shown also by looking at the behavior of different observables. Of course, this was expected because this is an integrable problem. But then let me tell you, just in the last 5 minutes, one result that I think it's very interesting and that we still have to exploit a little bit more. There is no Gibbs-Boltzmann equilibrium because although there is a stationarity, can be shown by looking at correlation functions and so on, one very clear way to see that there is no FDT, there is no equilibration a la Boltzmann, is that there is no fluctuation dissipation theorem. So what I'm doing here is, for example, I'm comparing linear response to the derivative of the correlation divided a potential temperature, and it doesn't work. There is no way to match the two. And if I do our nice construction of the integrated linear response against the correlation that in equilibrium should be a straight line, well, it definitely is not a straight line. Okay? So there's no single possible temperature description of what's going on here. Now, when I gave a talk about this here 2 years ago, not about this, about related feature in the quantum context, Robert Koenig, who was in the audience, and I showed something like this, not so horrible as this, but something similar, he said, but are you sure you cannot extract the temperatures of the GGE from these kind of measurements? And it turned out that yes, one can, and we had noticed that in the past, but we didn't exploit it actually, with Laura Foini and Andrea Gambassi looking at a spin chain, quantum spin chain. So then, okay, we came back to this issue, and let me show you how it works. So let me show you how it works in this problem here, which is simpler to discuss. In all of the phases that I showed, the Lagrange multiplier reaches a constant. It has oscillations at the beginning, but after a while, it goes to a constant. The value of the constant depends on the phases, but this is not important. It goes to a constant. If it goes to a constant, the frequencies of the oscillators go to constants as well, right? So in that limit, when this goes to constants, the modes decouple, and they become independent harmonic oscillators. So there is a time scale, I don't know exactly how it goes, but okay, there is a time scale, after which the problem becomes one of independent harmonic oscillators. If I have independent harmonic oscillators, after that time, their energies are conserved. And from those energies, I can compute mode temperatures, okay, just by equipartition, because these are oscillators. So for each of the oscillators, I have a temperature T mu. Now, this is the spectrum of temperatures. It's not constant, because there is no single temperature that describes the behavior of the problem, but okay, it has some form. Looks not very nice, but this is the spectrum it has for this particular quench I'm considering here. Now, imagine that instead of working with t mu's, I invert and I work with beta mu's. In this plot here, the red curve is the inverse of this plot, and it's also reversed in this sense. So this is the red curve over there. And the black curve is the FDT ratio for this problem in the frequency domain. So before I was showing it as a chi over C, chi versus C construction that we always find very useful in the case of glasses. Here it's not very useful to do it this way. It's better to do it this way. I'm just doing the ratio between response and derivative of the correlation function, but in terms of frequency. And this defines an effective temperature as a function of frequency. Just a second. This is the black curve there. Yeah.
Are these temperatures different because you have chosen the frequencies to be different?
I didn't understand the question.
Initial frequencies.
Yeah.
This harmonic oscillator.
Yes.
Chosen to be different. Is that why the temperatures are different?
Yes, exactly. So this is why the temperatures are different, is because these are the eigenvalues of the matrix of interactions. You see, when I linearize my problem, when I go to the basis of eigenvectors, this interaction becomes lambda mu is mu squared, sum over mu, and this is sum over ij, I different from j. Okay, so this is just an identity where the lambda mu's are the eigenvalues of this matrix. So each internal frequency of the oscillators depends on mu. It's different from each of the oscillators. And then this gives rise to these different temperatures, and these are the temperatures which are there. Okay. So, okay, don't pay attention to this orange line because it's some analytical approximation which is a bit too rough in this case. But what I want to stress is that the black and the red curves are the same. So, I don't want to show you how this works, but it's very easy to prove actually for an oscillator that this will happen. That there will be an identity between the temperature that you get from the fluctuation dissipation ratio as a function of time and then frequency, and the temperature that corresponds to equipartition, which is also the temperature that will appear for the oscillator in the GGE if you use energy of the oscillator as its conserved quantity. Okay, this is an extra point. So this can be done in different cases, and in all cases works fine. As I say, once you are in the limit of the independent oscillators, it's an identity. In the numerics, of course, we are not in the so long time limits in certain cases, and then there are slight deviations, and then also doing Fourier transforms in these discrete time intervals is kind of complicated, so there are several deviations, but the thing works fine. Okay, I'll jump over that, I'll jump over this. So I'll finish. So the question we are interested in is, we showed for this problem, it was quite obvious, that it was not going to be described by the Gibbs-Boltzmann distribution. Now the question that remains is, does it approach a generalized Gibbs ensemble? I still didn't answer this question. I haven't answered it yet. So a candidate, of course, is this one with the I mu's of Uhlenbeck and effective temperatures GGE that should be fixed within this GGE construction by the initial conditions of the same conserved quantities. So the construction tells you that what you have to do to fix the beta mu GGEs is to compute the average of the I mu's under this distribution and to compare to the values that they had in the initial instant, because later on they are conserved. So they keep the same number, the same value. So there should be, if this representation describes the long time limit, should be given by this average as well. So this is the way that people use to fix the values of the Lagrange multipliers, and in certain cases it works, but it's not obvious it should work always. Now, I showed you a way to extract beta mu's from the energies of the independent oscillators, but this is not obvious that these are going to be the same as these ones, because the I mu's and the E mu's are not obviously related either. There are certain relations that one can more or less guess, but it's not completely the same thing. And okay, we are working on that, but I cannot give you a definite answer for that. Just to give you an idea, so the blue points here are the values of the energies, and the red dots are the values of the I mu's. And this is in different sectors of the phase diagram. So, okay, there's something to be understood still here, but it's a promising model because we know a lot of things about them, about it. So, okay, let me conclude. It's time to finish. So very quickly at the end, I showed you the dynamics of classical isolated disorder models. We showed that they can equilibrate to Gibbs-Boltzmann measures if there are sufficient interactions within them, like in P = 3 cases. They can also undergo non-stationary aging dynamics by tuning the energy injection that one does, or extraction that one does. In other cases, they can probably approach a GGE, but there are still things to understand there. Whether one case or the other one is realized, it depends on the model, it depends on the kind of quench performed. And what we're doing now is to try to understand better this GGE formulation. And, well, we can also construct quantum P = 2 and do the same kind of things for these disorder problems at the quantum level. And it's a nice technical problem. There are still some issues to understand there, but okay, it's under reach. I mean, it's something that we will do. So, thank you. What do you think?
One of the ways to hope to make progress in this thing is, I don't know. I mean, this is sort of, so, in some sense, you have a dynamical system. I'm thinking about P = 2 with n integrals of motion in motion and so on and so forth. And so the question is whether this, you have a GGE. So
right.
Suppose, would it make sense to really add an additional Langevin noise to the dynamical equations, but then consider the limit that t goes to 0, which might just smoothen out things? And would that first of, because then you allow the system to equilibrate a little bit, so, but maybe in the limit that t goes to 0, you recover.
No, I can tell you what happens for t = 0 and the P = 2 model. We looked at it with David Dean in '94. So it's equivalent to coarsening. I mean, it's equivalent to the ON model.
But what you're doing is you basically start with an initial distribution of initial conditions. It is taken from a heat bath, and you just basically perform a quench.
Yes.
And then you're asking what happens, and then after the quench, you just evolve the systems as classical dynamics.
Yes, this is what I did.
So now instead of evolving this at this point, I'm saying add another temperature and Langevin noise, and then let that temperature go to 0.
Yeah, but it will coarsen. It will coarsen. Yes.
This is definitely.
It will coarsen in the sense that it will try to project in the direction of the IM vector, this one here. So what the spin will do, the vector spin will do, is it will try to orient in this direction. So it will come here. It will never reach the weight that it has to have to be in full equilibrium. So in full equilibrium, S should be √n times Vn. It will not reach this in times that don't scale with n. But apart from that, it will try to go in that direction. And condensing in this direction is associated to growing the 0k wave vector mode in coarsening. So this is the connection. So it will, So you destroyed,
P = 2.
Yes.
Linear dynamics.
P = 2.
When P = 2, then the Langevin dynamics will be linear or?
As linear as here. I mean, the only non-linearity comes through the Lagrange multiplier.
So P = 3 will become non-linear dynamics?
Yes, because larger than 2 is non-linear because in the Langevin equation you have two spins.
Does that have any, this thing that you're saying that for P = 3 it reaches the Gibbs-Boltzmann measure?
Yes.
Does that non-linear dynamics you think have anything to do with that?
Oh yes, sure. It has to do with the interactions It has to do with interaction potential that determines the force in your dynamics, and having this non-linearity in the force is the thing that, yeah. In the p equals 2 case, the only non-linearity is hidden in the Lagrange multiplier, and it's not sufficient to make it equilibrated. Yeah.
Okay.
So.